Hello, welcome to another module in this massive open online course. So, in this module, let us look at yet another very interesting application of linear algebra, analysis of linear systems, and that is a very powerful algorithm which is known as music algorithm. And do not worry, this is not music in the traditional sense, although in the sense it is also related to signal processing. The music here is an acronym which essentially stands for multiple signal classification. Okay, so, this music essentially stands for multiple multiple signal classification. And what is the music algorithm used for? This is used basically for DOA or direction of arrival estimation, which has naturally significant applications in practice, that is to estimate the direction of arrival of a particular signal. This is termed as DOA, that is the direction of arrival, and the music is essentially an algorithm Music is basically an algorithm for direction of arrival estimation, that is to estimate the direction of arrival of a signal, and you can see naturally this has significant applications in practice to estimate the direction wherein a signal is coming from, and hence the direction of the object which is emitting that signal, for instance be it either a ship or an aircraft, and naturally you can see this has several applications, for instance in the tracking of civilian aircrafts or in the tracking of fighter jets and so on and so forth. So, has a lot of applications, right. So, this has a lot of applications in estimating the location of objects or applications, what we call as ranging. Or we can simply say estimating the direction objects such as, for instance, ships or airplanes, etc. Now, first let us develop the model because the model is rather interesting and involved. So, let us spend some time on developing the model for this music technique. So, what is the model for this music technique? And the model can be described as follows, and this involves multiple antennas. So, to estimate the direction of arrival, naturally you need multiple antennas, so that you can differentiate the signals arriving from different directions. And let us say there is an object such as, for instance, an aircraft that is, so this is my cartoon of an aircraft that is emitting these signals which are coming at a direction of theta. So, this is essentially your direction of arrival, right. This is essentially your antenna array, with L antennas. This is the receiver, right. And an important parameter here, let us say we have L antennas in this antenna array. An important parameter here is the distance between the antennas. This is termed as D. D is the separation between. So, D here is essentially the D, this is basically the separation between this is essentially the separation between the antennas, and what we are saying is this D, that is this separation between the antennas, is fixed. That is, these different antennas are spaced at a this is an array of antennas, a linear array, and the spacing between the antennas is uniform, that is D, and therefore, this is also known as a uniform linear array. Okay. So, more specifically, this is known as a ULA. ULA stands for, and this is a very important concept in signal processing, a ULA stands for a uniform linear array, implies, which essentially implies that array is linear plus spacing between antennas is uniform, which is equal to D. The spacing between the antennas is equal to D. And now, let us consider the signal that is arriving at the first antenna to be x t e raised to minus j 2 pi f c t. That is the signal that is arriving here to be x t e raised to, or x t, you can say x t e raised to j 2 pi f c t, plus of course there will be the noise. So, let me draw this again just to illustrate this clearly. So, you have the antenna array and you have the signal that is arriving at an angle of theta, and this is the distance between the antenna elements D, and this is the signal x t. You can say this is x t into e raised to j 2 pi. This is the signal at the first antenna element, that is x t into e raised to j 2 pi f c t. So, we have y t. So, the signal at the first antenna is, we can write this as y t or y 1 t, if I call that as the signal arriving as the output signal at the first antenna. So, this is essentially your y 1 t, this will be your at the second antenna y 2 t, and so on, and I can therefore write y 1 t equals x t into e raised to j 2 pi f c t plus the noise, all right, or the noise that is N1 t, that is the noise at the output of the first antenna. So, this is output signal at this is the output signal at antenna 1, and this N1 t naturally this is the noise at antenna 1. This is the noise at antenna 1. Okay, very good. And now we ask the question, what is the signal y2 t which is the output of antenna 2, and naturally you can see the signal at antenna 2 will be related to antenna 1, and in fact the signal at antenna 2 is going to be a delayed version of the signal and at antenna 1, and how do we capture this in our model. Okay. So, you can see the interesting observation that signal at antenna 2 is a delayed version of the signal at antenna 1, and we would like to capture this. How do you capture this? How do you capture this phenomena? And the idea is very simple. If you look at the difference in the distance, right. So, this is basically your d, and if you look at this is angle theta, and therefore, this distance, if you look at the difference in the propagation distance, this is equal to d cosine theta. This is the difference in propagation distance. So, the difference in propagation distance at antenna 2, we have difference in propagation distance is d cosine theta, which implies the delay. This is interesting, the delay is distance divided by velocity. So, this is equal to d cosine theta divided by c. So, at the signal at the second antenna, the signal is delayed by this quantity d cosine theta over c, where d is essentially, if you remember, this is the interantenna spacing, theta is the angle of arrival, right. Remember, that is the direction of arrival. Okay. Now, therefore, the signal y2 t is going to be the same signal x t times e raised to j 2 pi f c, and now the delay is captured by t minus the delay, which is essentially d cosine theta divided by c, plus of course, the noise is going to be independent, right, because this is the noise at a different antenna. And now, I can write this as x t e raised to j 2 pi f c t times e raised to minus j 2 pi f c d cosine theta over c plus n 2 t. Now, use the property c by f c is equal to lambda, right. What is lambda? Lambda is the wavelength of the carrier. Implies this becomes, implies if you look at this, you have the 2 pi f c d cosine theta over c. I can write this as, well, d cosine theta over c, c by f c is lambda. So, I can write this as 2 pi d cosine theta over lambda, or 2 pi d over lambda cosine theta, which I can write as k, some constant k times cosine theta, where k equals 2 pi d over lambda. And therefore, now if you look at this, this becomes y 2 t equals y 2 t equals x t e raised to j 2 pi f c t times e raised to minus j 2 pi f c d cosine theta over 2 pi f c 2 pi d cosine theta over lambda plus n 2 t, which I am writing as which I am going to write as x t e to the power of j 2 pi f c t e raised to minus j times k cosine theta plus n 2 of t. Okay. And similarly, so essentially we are using the property that where you have the signal received at the second antenna is a delayed version of the signal received at the first antenna, and in fact, if you look at this, that delay depends on the angle theta, right, because it depends on cosine theta, and it in turn translates into a phase difference. So, there is a phase difference, you can clearly see that in the received signal. So, there is a phase difference, right. So, there is a phase difference. Now, similarly, you have y 3 t, this is equal to x t e raised to j 2 pi f c t minus, now the delay is going to be 2 d cosine theta divided by c plus n 3 t, which is equal to x t e raised to j 2 pi f c t e raised to minus j, which will be e raised to minus j 2 pi 2 d cosine theta over lambda plus n 3 t, which is essentially equal to x t e raised to j 2 pi f c t times e raised to minus j 2 pi e raised to minus j 2 k, right. This is 2d cosine theta or lambda. So, this will be 2 k cosine theta plus n 3 t and so on. And therefore, now one can summarize this model by writing y1 t, y2 t, so on up to yl t, that is the received vector, right. You can think of this as the output vector comprising of the signals from the L antennas. Output vector of signals from L antennas, this is equal to x t e raised to j 2 pi f c t times, you will have the vector of phases 1 e raised to minus j k cosine theta e raised to minus j 2 k cosine theta e raised to minus j L minus 1 k cosine theta, all right. So, plus the noise vector, which is you have your the usual n1 t, n2 t and n of L of t, noise samples for the different antennas. And therefore, if you now look at this, the interesting thing about this is this I can write this as my vector a bar of theta. So, I can write this as the vector a bar of theta, and you can see this a bar of theta, this has an interesting structure. Let me just write this again over here. This has a graded phase constant phase offset of e raised to minus j k cosine theta with respect to e raised to minus j k cosine theta, e raised to minus j 2 k cosine theta, e raised to minus j L minus 1 So, this depends on theta, as you can see. This is an L cross 1 vector, and this is it depends on theta, right. So, it captures the, you can clearly see it captures the effect of the direction of arrival theta, right. It is the signature of a signal that is arriving with a direction theta at the array, and this property can be used to estimate the direction of arrival of the signal at the receiver. So, this is known as the array response vector, which is a function of theta, or this is also known as the array steering vector with respect to the direction of theta, or the spatial signature of the array corresponding to the direction theta. So, the interesting thing about this is this captures, this is the spatial signature, right. It is the signature this is the spatial signature of a signal arriving at a direction theta. This is also known as, so this a bar theta, this is also known as the array response vector, or this is also known as the array steering vector, and this has an important role to play in array processing, right. So, array response vector, this is very useful in the entire area of array processing, and music is an algorithm for the same array signal processing, right. The broad area of array signal processing, which music belongs, is one of the algorithms that can be used for array signal processing, that is signal processing using arrays, which was in fact a revolutionary step forward, moving from signal processing using a single antenna. That is, we have a single antenna receiving the signal, and what has been discovered, in fact what as we are going to see in this music algorithm, that once you use an array of received signals and process the signals collectively, then that can lead to much better, significantly improved performance, and of course newer applications, for instance such as direction of arrival, determining the direction of arrival, which you can clearly see is not possible with a single antenna, because if you have a single antenna with a uniform response throughout at all angles, right, it is not possible to determine the direction of arrival using the signal received at the single antenna. On the other hand, when you have these multiple antennas, you can clearly see there is a signature corresponding to the angle of arrival theta of the signal, and this can be used to determine the direction of arrival of the signal, as we are going to see in the music algorithm. Okay. So, this is the array steering vector, and this is unique for theta, right. This is unique for each theta, that is the interesting property. This is unique for each theta. Okay. And therefore, now I can write this as y bar t equals a bar t x t e raised to j 2 pi f c t plus n bar t. Now, once we sample this, now the sampled version of this, right, sampled version, the digital signal corresponding, sampled digital signal can be written as y of m equals a bar theta times x of m plus n bar of m, where you can think of m, that is if you have the sampling duration mt, this is at t equals, you can think of this, although we will not dwell on this, t equals the sampling interval which is 1 over f s, that is the sampling frequency, okay, which is not very important, but the point is you can write this as, this is the model, that is y bar of m. Let me make this correction, this is not, this is a vector, y bar of m equals a bar of theta into x m plus n bar of m. And now if you have multiple signals, if you have p targets, now extend now let us consider p targets, and this becomes with the signals, and the DOAs of the p targets can be theta 1, theta 2 up to theta t, and the signals can be x1 m, x2 m, so on xpm, and this implies that the multiple signal model, so will be the superposition of all of these, that is x1 of m a bar of theta 1 plus x2 of m plus x p of m a bar theta pli plus n bar, which I can write as the matrix y, which I can now write as, using the matrix notation, y bar of k, or rather y bar of m equals a bar theta 1, a bar theta 2, so on a bar theta p times x1 k, x2 k, that is the symbols. Times x1 m, x2 m, x p m plus n bar m. This is the vector, this is the matrix representation. As usual, this is the matrix, you have p DOA vectors, each of size L cross 1. So, this will be, matrix will be of size L cross p matrix. This is a p cross 1 vector. This is, whenever you write a linear model, it is good to do a check, always do a check to make sure that all the dimensions are correct, right, the dimensions should match. So, output is p vector, output is vector of size p, input also has to be a size of vector p. In fact, this is your matrix. I can now call this as the matrix A theta bar, and therefore I can call this as your vector x bar of m, and therefore I can write this model as implies y bar of m. Now, with the multiple signal, this becomes A theta bar times x bar m plus n bar m, and this is now your multiple signal model. Okay. So, this is basically the multiple signal model. This is basically your multiple signal model, and now we want to classify this, implies we want to, the classification is basically determining these directions of arrival theta 1, theta 2 up to theta p, right. So, these are the directions of arrival of the p signals. We want to determine these DOAs, right. So, we want to determine these, and this is nothing but the classification. This is essentially what is termed as the classification part. So, essentially you have multiple signal model. So, multiple signal model which is given above, plus the classification aspect, and this essentially gives rise to your algorithm that we are going to talk about, which is the music, that is multiple signal classification. How do you use this multiple signal? This array, antenna array comprising of these array response vectors of the p targets, right, corresponding to the p directions of arrival. Use this multiple signal model and actually classify these signals, that is determine these directions of arrival theta 1, theta 2 to theta p. This is essentially your music algorithm, that is the multiple signal classification, which we will explore in the next model. So, this is the system model. Starting with this, we are going to explore or discover the music algorithm. Thank you very much.